Welcome to this tutorial on importance sampling. This is an important algorithm that gets applied in many areas of science and business that ranges from risk management, rare event modeling to just being an efficient component in many other machine learning algorithms, including modern deep learning. That said, the name is kind of a misnomer because it is not necessarily a sampling algorithm. Rather, it is a trick that helps you compute expectations and provide solutions to intractable integrals. Since the central object in this story of importance sampling is the expected value, let's spend few seconds so as to be on the same page as far as the notation is concerned. Expectation or expected value of a random variable is essentially a weighted average. Here I'm showing the general formulation for both discrete and continuous random variables. In these equations, h of x is the function of random variable x and p of x is the probability distribution function for the random variable x. For the probability distribution functions, I'll be using either p or q, and the function of random variables will always use h. The probability distribution function will always be on the rightmost side of the integral, and also note the subscript of e, which indicates the function which is our distribution functions. So in this case it is p. The notation part out of the way, the main struggle with computing expectation lies in the fact that we are going to be dealing with intractable integrals, at least in this current formulation. And the remedy for this challenge lies in using a law called the law of large numbers. This law simply states that if we can conduct large number of trials and if we can sample from our distribution, then we can approximate the expected value using a simple average. So this is a way around the challenge, but then the new challenge is what should be the value of n? How many number of samples we should have in order for this law to hold? Does it also depend on the distribution function or the function of the random variable, or maybe both? That said, one important aspect is that we should be able to sample from the distribution in order for this law to be even applied. And that brings us to appreciate the three main challenges associated with the expected value computation. The first challenge is related to the sampling aspect. Here the difficulty stems from the fact that we cannot sample from the distribution p, and as a consequence will not be able to apply the law of large numbers. And maybe we can sample, but the procedure happens to be extremely inefficient. Inefficiency in sampling context primarily translates to generating many samples to reach convergence. Requirement to generate many samples means more computation time. On top of that, these large number of samples typically introduce large variances. Another associated aspect related to inefficient sampling is about computing rare event probabilities. Since a typical sampling procedure should follow the distribution, that is, it should generate more random variables that have high probability of occurrence, this creates the inefficiencies when we are interested in rare events. As the name implies, rare means low chances of happening, and hence we would be sampling less in those areas, and therefore indirectly we would require a large number of samples to even get to computing these rare event probabilities. Now, importance sampling provides a solution for these kind of problems as well, and is therefore often categorized as a variance reduction algorithm. In the previous challenges, we have assumed that despite having sampling problems, at least we can compute the probabilities. In other words, we are working with normalized distribution. Unnormalized PDF means that we do not know the normalizing constant, or we do not know how to compute it, or we may know how to compute it, but computationally it is not feasible. This typically is the case when doing Bayesian inference, where the posterior distribution is unnormalized. We will explore how importance sampling accommodates this kind of a challenge as well. So here is our central object yet again in the middle, and to address the first two challenges, I am considering the scenarios in which, while we cannot sample from the distribution of our random variable shown here as p, we can evaluate its density function. That is, given a sample x, we can get the result using the function p. A general theme that runs in Monte Carlo based sampling techniques is that if we cannot sample from the distribution of our random variable, then we should use a proxy distribution. This proxy distribution is called a proposal distribution or a sampling distribution. And we then either use an acceptance criteria and or adjust for the fact that we have sampled from another distribution. That said, we can choose a proxy distribution, which is easy to sample from, but we still have to bring it into this expectation object. And here is our first step in that direction. Doing this does not impact the integral, as all we are doing is that we are multiplying it by 1. Some literature calls it a probabilistic one. Q is the symbol for our sampling distribution. Here I have simply switched P and Q. If you recall, I mentioned that in this tutorial, the rightmost place in the integral is reserved for probability distribution, which also means that we should change the subscript in the expectation symbol to Q, as distribution function Q is now our sampling distribution. And because of this little rearrangement of our function of random variable has also changed, and we indicate that by using H prime. The ratio of our original PDF and the sampling distribution PDF is called likelihood ratio, and in the context of importance sampling, it is known as importance weight. Essentially, it is the factor that introduces the correction to account for the fact that we have used a proxy distribution for sampling. And finally, thanks to the law of large numbers, we can write this newly formulated expectation as this. As you can appreciate, this was simply a rearrangement in the expectation equation. However, the big question should be about the choice of the sampling distribution Q and its parameters. We will get some answers to this question by working through two exercises. As part of these two exercises, I will show that many other problems that involve integrals can be represented as expectation and therefore can benefit from law of large numbers. I have also not yet emphasized on the significance of the word importance in the name of this algorithm. This will also be uncovered as part of our exercises. So without further ado, let's see our first problem. Here I have a function h defined like this, essentially a simple symmetric exponential function. The problem we want to solve is to compute the integral of this function, or area under the curve, between 0 to 10. Now, this is an integral that I can solve manually, and I know the solution or the true value of area under this curve. And I would like to do that because this would help me in evaluating how well our sampling based solution is going to perform. That said, there is an integral here, but this problem does not translate anything like our expectation object. An expectation is supposed to have a function of random variable as well as the probability distribution function. Here in this integral, we only see the function of a random variable. So our first order of business is to represent this integral as an expectation. And for that, we would need the probability distribution. And the distribution that I will choose is the uniform distribution because its PDF does not depend on X, and I can do this kind of a trick. Here I am writing the PDF of uniform distribution indicated as P of X, which is equal to 1 over 10. If you are not familiar with the PDF of uniform distribution, I would recommend to first check it out on Wikipedia, else this entire discussion would not make sense anyways. Since PDF of a uniform distribution is constant, we could achieve this kind of a trick. Now, writing it using the functions, you can see that we now indeed have an expected value formulation, which is simply scaled by 10. And here is our final equation taking into consideration the law of large numbers. And you can see that I also have plotted the curve for the uniform distribution, which is just a straight line. I then ran this experiment for different values of n, and let me show you the results. The first result shows the plot of the expected value given the number of samples. We start to consistently see the value of around 1 when we have 10,000 or more samples. I also plotted the variance in the computing the expectation, and it starts to stabilize but still remains at around 4, which is a high variance. Clearly, this experiment shows inefficiencies in sampling. Now, so far what I have shown you is classified as standard Monte Carlo sampling, and now is the time to get creative and see how we will do this exercise using importance sampling. But before that, let's take a moment to grasp the notion of importance in the context of this example. So the goal with this exercise is to compute the area under the curve. There are two functions involved, h of x and p of x. P of x being the uniform distribution does not impact the result, as for all the samples the value remains the same, and hence the result is solely governed by the evaluation of h of x. This means that the major contribution to the value of our integral is coming from the samples that are in the middle of x-axis, indicated using orange crosses, because these are the places where the function results in a higher value or higher values. Because the usage of uniform distribution for sampling will generate random numbers between 0 and 10, you can see that a lot of time is essentially getting wasted by the regions marked as red. If we don't even sample from it, it would still not impact the result that we will get. But yet we end up spending a lot of time, or equal time, I suppose, in these areas because we have used a uniform distribution. With all this being said, we can say that for this given problem, the central part of our x-axis is the region of importance. Because this is where our samples should have came from. Most of our samples should have came from in order to be efficient in terms of solving our problem. And this, my friend, is the significance of the word importance in the name of our tutorial today. That is, we should select our sampling distribution Q such that it helps in sampling from a region of importance. Now, one distribution that we can see being efficient in sampling from this region of importance is the normal distribution with a mean of 5. As we can note that our function h of x peaks at a value of 5, and a normal distribution which is centered at 5 makes a fine choice. Normal distribution is also going to give low probabilities to the area where function also has the lower values, and hence, unlike uniform distribution sampling, normal distribution would mostly end up sample from the central part of our plot. I'm now writing the expectation as per our earlier importance sampling arrangement by making use of the probabilistic one, so that the normal distribution would become the sampling distribution, and we would correct the expectation with the help of importance weight. And finally, the law of large numbers as well. Nothing should surprise you here, as we derived all this earlier. Let's see how we fared this time in terms of number of samples and variance. Here is a curve showing that we reached the value of 1 around 1000 samples. Let's see it by comparing it to the previous experiment that did Monte Carlo sampling. And for variance, it really did well. The variance was quite low, as you can see, especially in comparison to uniform distribution. So with importance sampling, we were able to achieve our goal with just around 1000 samples. Before we do our next exercise, I want to emphasize that the region of importance depends on your problem. For this problem, it was in the middle of the function h. But it could very well be the case for another problem. This could have been the region of importance. And now we will see such an example. So for the new exercise, I have a new function and its plot looks like this. And for this problem, I know that x follows the standard normal distribution. So here is its plot as well. And for this given h and p, we are interested in knowing the probability of getting x greater than 2 or greater than equal to 2. That said, it again does not look like an expectation problem for a minute. It will translate into an integral, but very much like the previous problem, we first need to see it as an expectation problem so that we can apply the law of large numbers. And the second observation should be that this problem requires us to sample from low density portion. For standard normal distribution, anything beyond standard deviation of 1 is going to be a low probability zone. Let me get the first issue resolved, that is repose our problem as an expectation first. Here is how we write expectations generally. As per our problem, we should care only for samples that have values greater than or equal to 2. In other words, we should find a way to exclude rest of the samples, that is samples with values less than 2. And the way we generally indicate this mathematically or notationally is by making use of an indicator function. An indicator function essentially evaluates to 1 if the constraint is satisfied and 0 otherwise. When implementing using a programming language, you can either modify the h of x or simply multiply the result of an additional function that returns 0 when the constraint is not met. And doing this still keeps our expectation formulation intact. The interesting portion is really about the region of importance for this given problem. Sampling procedure will generate samples according to the chances of occurrence given by the PDF, and therefore will rarely get samples in the region of importance if we use our current PDF, that is standard normal. Again, appreciate the fact that even though normal distribution is pretty good at sampling, it will be an inefficient choice for our problem, for this very problem. These types of scenarios are what we called rare event probabilities, and sometimes we are indeed interested in knowing them. And next problem for us would be which proxy distribution to use in order to make sampling efficient. Now the plot should give you some hints. For example, you can visualize here that we should be able to use a normal distribution, another normal distribution, which is centered near 2 or 3. Or maybe somewhere in between 2 and 3, and that should help us cover the region of importance. That said, we could see this solution with the help of our plot or shape of our function, but maybe we should wonder if there is a way to determine it mathematically. And there is one possibility, not a perfect one, but there is indeed one. And it's called the maximum principle. The first idea is to choose Q such that it is similar in shape as h of x and p of x. Similar in shape often translates into choosing from the same distribution family as p. So for our current exercise, we should choose a normal distribution, but then what would be its parameters? One way to estimate the parameters is by evaluating where is the peak of the product of h and p. In other words, we turn this into a maximization problem. Let's do this quickly for our current exercise. Since we are selecting normal distribution for our Q, we need to primarily estimate its mu. Standard deviation is still assumed to be 1, but you can always play with that as well to get better efficiency. And after solving the maximization problem, the answer appears to be square root of 8, a number between 2 and 3 as we visually anticipated. Now, this may seem simple, but consider the situation when you have many maximas. So maximum principle does work in many situations. It should be one of the things you should try, but we cannot say that we have a unique solution. Therefore, as I earlier said, it's a solution, a good approach to start with, but is not perfect, especially for high dimensional and multi-model problems. And now let's use this Q, that is the sampling distribution whose mean is square root of 8 and is shown in its plot in green. You can see that it would be far more efficient in sampling from region of importance than our original distribution. The importance weights will do their magic to adjust for the fact that we have used another distribution for sampling. The steps from this point onwards are the same. I leave this as an exercise for you to try and let me know in the comments how many samples it took. Now let's talk about the third challenge, where not only it is inefficient to sample from P, but the P is not normalized either. Bringing our importance sampling formulation in the center again, if we cannot evaluate P of X, it means that we would not have importance weights. By the way, it is also possible the situation is true for Q as well. Well, maybe you should select Q which is normalized, but since I mentioned earlier that recommendation for choice of Q is that it should at least follow the same shape or distribution family as P, we may very well end up having a Q which is unnormalized, but we can sample from it. So we are in a bit of a fix here. And quite often the way to get out of this fix is to simplify our equations. So let me start with that and see if we can find a way out. Here I have written both P and Q in a slightly different notation. The tilde on the top of P and Q indicates that this function is unnormalized. The z or z's are the normalizing constants. Sometimes you can get lucky that they may cancel each other even when you have unnormalized P and Q. So that would work out. But we are considering the case when it would not be the case. Here is another simplification step. I have moved the ratios of z's out of the integral as it is going to be a constant, and I have applied the law of large numbers to it. And our troublemaker is still visible and staring right at us. Let me now try to deal with this troublemaker. I could rewrite it as following. All I have done is to expand it, and it would be an integral that would look like this. The normalizing constant is essentially a marginalized probability. I'm assuming you know this. Now let's see how we can replace zq with something else. On the left, I'm showing that zq can be expressed as the ratio of unnormalized q and normalized q. And substituting in our equation, moving this ratio inside the integral because it is a function of x, rearranging the fraction now, we can see that we have managed to express it as an expectation. The first term is a function of random variable and the second term is the distribution function q. And we can express this using the expectation notation as well. Subscript is going to be q and the function consists of ratio of unnormalized functions which we can evaluate. And finally, applying the law of large numbers. Pretty clever, isn't it? Essentially, we'll be approximating our constant as well using the law of large numbers. And this is how we get to work with cases when the distribution functions are not normalized, and there is even a name for it. And it is called self-normalized importance sampling. So is that all there is to importance sampling? I am sorry to disappoint you, but the answer is no. The topic of importance sampling and its variant is quite vast and sophisticated. I have barely scratched the surface here. I explained the fundamental ideas behind it and a variant of it, but there are many more variations and extensions that exist within this framework of importance sampling. Here I am showing you few variants that maybe one day I will make tutorials on. And once again, importance sampling does play a very key role as an algorithm on its own and as a component in other algorithms in machine learning. So understanding it is quite important indeed, and no pun intended. This brings us to the end of this tutorial. I hope I was able to build your intuition as well as clarify the formulation behind importance sampling. As always, if you have questions and doubts, please do write them in comments and I will try my best to answer them. Finally, I want to thank you for the time that you spent here in this tutorial and wish you all the best in your learning. Goodbye for now. See you in another But What Is tutorial.